Hello, my name is Paul, and today I'll be talking about the basic of how sound travels in the ocean in the short video presentation. And I hope you'll have a better understanding of ocean acoustic after this presentation. If you have taken a physics class, you would know that the speed of sound on average is around 343 meters per second in the air. And anything faster than the speed of sound will be given a Mach number associated with it, and you will also have the sonic boom phenomenon happening. But what about the speed of sound in water? Is it 343 meters per second also? Well, the speed of sound in the water is actually about 1484 meters per second, but the general conception is that it is known for being 4 times faster than the air. This is particularly due to the nature of the water particles being closer than the air particles, so that the particle can carry out the sound faster in water than it can be in the air. But what dictates the speed of sound? In the atmosphere, you might recall that the speed of sound in the air is dependent on the pressure, or the atmospheric pressure. In the ocean, it is controlled by 3 main factors: temperature, how hot or cold the water is; salinity, how fresh or salty the water is; and pressure. But since pressure increases linearly in the water, this can be also as denoted as depth. An increase in temperature will lead to the increase of speed of sound. An increase in salinity would lead to the increase in speed in sound, and as you might have guessed it, an increase in depth would also lead to the increase in speed of sound. So then, an increase in any of these 3 factors will lead to an increase in speed of sound, or in oceanographic terms, they call it celerity. But not all parameters are weighted equally, so which one of them will have more of an effect on celerity? First, we'll look at the equation that dictates the speed of sound in the ocean. Here's the general equation. There is a more accurate equation, but this equation serves its purpose for this video. What this equation describes is that the celerity of sound wave in the ocean is proportional to the temperature, salinity, and pressure of the oceanic environment. In the equation, C equals to the celerities in meters per second, temperature is measured in degrees Celsius, salinity is in parts per thousand, and the depth of water where the sound originated is measured in meters. Let's break down the equation for a bit and look at it in more detail. Here I've highlighted the parameters. As you might already notice, the speed of sound in the ocean is greatly influenced by temperature. The average salinity in the ocean is 35 parts per thousand, and it fluctuates around 34 to 36 parts per thousand. It might be safe to say that salinity doesn't have a big impact on the speed of sound in the ocean, but what we can get from this is that fresher water is slower than saltier water. There is a common misconception to note is that density, being a factor of temperature and salinity, is not the parameter that influences the speed of sound in the ocean. It is only temperature and salinity. Now, to put it into a perspective of a general speed sound profile in the ocean. The surface tends to have the highest speed because it is the warmest in the thermal gradient, and it decreases with increasing depth because the water gets drastically colder in the thermocline. But there is a part of the ocean where the speed of sound remains relatively the same above the thermocline because the decrease in temperature and the increase of depth cancels out each other. As you all know, the temperature of the ocean has little thermal gradient at the bottom. This layer is called the deep isothermal layer, but there is an increase of pressure with depth, so the speed of sound decreases slowly as you move from the bottom of the ocean to the top. So, this means that there must be a zone in the layer of the ocean where the speed of sound is at its minimum where the two lines will intersect, and that this place is called the deep sound channel. It's also known as the sound fixing and ranging channel. There are important implications for this phenomenon, but first, we must explore some other concept of acoustic which will tie into all of this. It's important to note that what I have just previously described does not satisfy all places on Earth. Recall previously on what I said about the ocean surface condition. It's warm. But what happens if it isn't warm? Well then, we will have a different vertical sound profile. And at what place would the water be cold at the surface? And there's only one place on the Earth where there's cold on the surface, and that would be the polar regions. Here is the sound profile, which also includes the polar region. As many of you might already know, the polar region is where the deep water circulation forms, so that the temperature and salinity profile would be relatively the same throughout the vertical layer. So that means the only thing that controlling the speed of sound in this region would be the depth. One important concept that we have to revisit is the Snell's law, or known as the refraction law. Snell's refraction law states that whenever a wave passes through from a faster medium to a slower medium, it will bend toward normal. Now, what does it mean exactly? But in a sense, it means that depending on where you are in the ocean, the sound being emitted will end up in different trajectories. This diagram shows various trajectories of the sound wave in the ocean and places where it originates from. The dashed line on the left indicates the speed profile in the ocean. An important point to remember is under Snell's law, waves will bend towards the region of no sounds or bend away from the region of high sounds. Point A is a scenario where the sound originates from the polar region. In this region, sound will stay around the same area where the speed of sound is the minimum because of Snell's law. In the other picture, similar cases can be described in path B and C as well. But in case of point D and E, the steeper angle of propagation can result in a more complex path which does not support the long-distance propagation. And scenario F is a propagation at the continental shelf where the speed of sound is at its maxima, so that it propagates in a zigzag direction. But what is the boundary of the deep sound channel? There needs to be a condition for the deep sound channel to support long-range propagation of sound wave, and that is the critical depth. A positive critical depth is where the sound speed profile at the bottom exceeds or equals to the sound speed profile at the surface. This denotes the upper limit of the deep sound channel in yellow, while the other denotes the lower limit of the deep sound channel in purple. Likewise, a negative critical depth is where the sound speed profile at the bottom is less than the sound speed profile at the surface. In that case, the bottom of the ocean would be the lower limit of the channel. A positive critical depth will allow the sound propagation to travel for a long distance without bottom interaction, where there will be no scattering and no reflecting will occur to the sound waves. So, why is the deep sound channel important? For one, it has implications on the naval arms race and the presence of submarines during the Cold War. During the Cold War, the United States and Britain had dedicated most of the defense for the Atlantic in the GIUK gap by placing sound sensors in the deep sound channel to pick up signals of Soviet submarines. This phenomenon also allowed marine animals to communicate over a long distance through low-frequency sounds as mentioned earlier. Many whale species use this channel to communicate across the Earth. Some contemporary usage of the deep sound channel is by placing a hydrophone in the middle of the channel. Many different sounds can be picked up, which includes the previously mentioned topics, and earthquakes and man-made noises, which prove to be an important monitoring system for the ocean. That's it for what I have to say about the acoustic in the ocean.